Okay, Chem 345, March 27th, take 2. Sulfonation, desulfonation, nucleophilic aromatic substitution, and the Benzyne reaction. Hopefully this time around it's going to actually have audio. Sorry about that. Okay, so let's start off with sulfonation. Sulfonation is an example of an electrophilic aromatic substitution. Where we add sulfuric acid and sulfur trioxide, and together these add a sulfonic acid group to a benzene ring. Now the mechanism is very similar to all the mechanisms of electrophilic aromatic substitution. First thing you do is you create an electrophile. Then the benzene ring attacks. And then the third step is deprotonation to reform the aromatic ring. So in this case, the electrophile is just going to be activated SO3. And so the way you activate the sulfur trioxide is you protonate it with sulfuric acid. Now this is the electrophile. And this is what the pi system reacts with. So the pi system's electrons add to the sulfur, and electrons go up to the O. And as a result, we get the sigma intermediate, and then the last step of this reaction is some base comes and takes that H off. It could be the conjugate base of sulfuric acid. It could be another molecule of SO3. Either one. And as a result, you end up with that. Now, what makes sulfonation so unique among the electrophilic aromatic substitution reactions we've covered is this last step right here. This last step can actually be reversible. And so this gives us another reaction, mainly the desulfonation. Now, to do the reverse reaction, you need similar conditions, such as strong acid. You don't need SO3 because that drives the reaction forward. If you want to drive the reaction backwards, we're going to add water to that. And also, this is not that favorable of a reaction. So you do need to add some heat to get it to go. And that basically removes the sulfonic acid group. So, the mechanism of this. Is the reverse of this mechanism. So the last step in the mechanism is deprotonating the sigma intermediate to give the aromatic ring. So the first step is we're going to protonate the aromatic ring to give the sigma intermediate. And so this is a little bit unusual that we are going to actually protonate the benzene ring, only we're not going to protonate it at the ortho, meta, or para position. Instead, we are going to protonate at what's called the ipso position. That's the carbon attached to the group itself. Ipso. That's fun to say. Ipso. Okay. So, these electrons grab that hydrogen. Electrons go up. That forms the carbocation intermediate. And then you use the electrons from the OH to swing down, and they kick the carbon-sulfur bond over to establish the benzene ring. And now is where we get to the purpose of having the water. SO3 is very hygroscopic. It absorbs water. And so once this is formed, water attacks that. And then followed by deprotonation. You have 2 molecules of sulfuric acid. And this drives the reaction forward because you're generating more acid to do this first step, and you're also absorbing more of this sulfur trioxide, driving the reaction forward, and that's what eventually removes all the sulfonic acid groups. Now, this is actually a pretty useful reaction, being able to put on a group and off a group. So, I'll give an example of a practical use of this. Let's say you take a benzene ring and rebrominate it. And then let's do the sulfonation. Now, bromine is an ortho-para director, so the major product is going to have the sulfonic acid para to it. Then if we brominate again, we now have 2 groups on this benzene ring, the sulfonic acid group and bromine. Of these 2 groups, bromine is the most activating group, so that's the director that we're going to use. It's an ortho-para director. The para position is blocked, so the bromine goes ortho. Now if we do the desulfonation process, heat, acid, and water, We do the desulfonation process, and we get this. An orthodisubstituted compound. Now, we just add 2 bromines. It seems like a roundabout way, but if we were to add it traditionally, the major product would likely be the para-disubstituted bromine. So you can think of the sulfonic acids, because they're easily removed on and off, you can think of these sulfonic acid groups as a protecting group. And what they specialize in protecting is they protect the para position. So if you need to get 2 groups ortho to each other, this is a good way of going about it. Okay. Now, let's take a look at nucleophilic aromatic substitution. Now, this is very similar to what we have been doing, only just everything in reverse. Instead of attacking aromatic rings with electrophiles, nucleophilic aromatic substitution, or what the abbreviation is SNAR, attacks aromatic rings with nucleophiles. Now, in order for this to work, is your nucleophile, well, actually, I should say your electrophile, in this case, your aromatic ring, needs to be electron deficient. What I mean by that is you simply take chlorobenzene and treat it with sodium methoxide. Okay, so, sorry, I had to pause that. If you treat the chlorobenzene with sodium methoxide and methanol, nothing really happens. But if the aromatic ring is sufficiently electron deficient, such as there's a nitro group on there, you treat it with sodium methoxide and methanol, you can actually displace the chlorine with a methoxy group. If it's the nitro is into 2 position, ortho to the chlorine. You can displace it. With that said, if it is meta to the chlorine, no reaction. So not only you need to have a strong electron withdrawing group, in this case a nitro group, you also need to have it very specifically located, either ortho or para, to your leaving group. So, mechanism of this. This mechanism is actually reminiscent of the carbonyl chemistry mechanism with a strongly basic nucleophile. This is not an SN1 mechanism, this is not an SN2 mechanism, this is an SNAR mechanism, where the nucleophile adds and you get a carbanion. And the resulting carbanion swings its electrons down and kicks off the leaving group. Now, if it kicks off the OMe, you're right back where you started from. If it kicks off the chlorine, you get your product. And this last step is fairly irreversible, especially when your leaving groups are weak bases, like chlorine, fluorine, bromine, and iodine. We'll get to that. First, I want to focus on this intermediate right here, this carbanion intermediate. This is sometimes referred to as the Meisenheimer complex. And the more stable that this intermediate is, the faster the reaction goes. Essentially, its energy profile looks something like this, of the reaction, where the rate determining step is the loss of aromaticity. Now, this is what's called a late transition state, meaning the transition state is closest in energy to the intermediate. That means the transition state here looks most like the intermediate. Another way of phrasing this is Hammond's postulate. You see this transition state, since it's late, it closely resembles the intermediate. And so the more stable the intermediate, as we lower the intermediate's energy, the transition state also is lowered, making the reaction go faster. And what stabilizes this carbanion is resonance. Now, you normally have 3 resonance structures, very similar to electrophilic aromatic substitution. But the key to this, and the reason why you need the electron withdrawing group, ortho or para, to your leaving group, is when it's ortho or para, you have an additional resonance structure where you can put the electrons up into the electron withdrawing group. This is a major resonance structure. This extra stability makes the reaction proceed much faster. If the nitro group is meta to it, you can't put the electron density up onto the nitro group. So, requirements for nucleophilic aromatic substitution. You need an electron deficient aromatic ring. And so what this means, in this course, you need to have at least one nitro group ortho or para to the leaving group, or need to have this type of motif. Aromatic rings like this are electron deficient. And the mechanism of these are going to be in the problem set. But you need to have it either your leaving group right next to it, so in the 2 position, right next to the nitrogen, or you need to have it in the 4 position, because in the resulting carbanion intermediate, it puts the electron density onto the nitrogen in these 2 patterns. Next thing you need is you need a leaving group. And the leaving groups are a little bit different than SN1 and SN2. See, if you look, the rate determining step in this reaction is this first step, the loss of the aromaticity. The leaving group actually leaving is not as important. Therefore, in the case of SN1 and SN2, the leaving group is part of the rate determining step. In the case of nucleophilic aromatic substitution, it isn't. It's in the 2nd step. And so the leaving groups that we need, the best leaving group that we're going to have in nucleophilic aromatic substitution is a fluorine. Fluorine is better than chlorine, which is better than bromine, which is better than iodine. The reason for this extra leaving groups is the fluorine has to do with electronegativity. The fluorine is more electronegative than chlorine. Chlorine is more electronegative than bromine. Bromine is more electronegative than iodine. This extra electronegativity inductively creates a delta positive on this, which makes it more attractive to nucleophiles. Next thing, next requirement is it really helps the nucleophile is basic. So a conjugate pKa greater than or equal to 10. That makes these reactions proceed much smoother. Are there examples of nucleophilic aromatic substitutions that don't have a basic nucleophile? There are, but those are exceptionally rare. The ones with a basic nucleophile are much more common. You'll see those a lot more. That brings us to the last reaction, which really doesn't have an official name, but sometimes it's referred to as like a Benzyne reaction because of an intermediate. At first glance, this reaction looks like a nucleophilic aromatic substitution. It really does. But this reaction is not a nucleophilic aromatic substitution. It is not synthetically useful either. It looks okay, but the problem is this lacks the necessary electron withdrawing group to do the nucleophilic aromatic substitution. When I mean it's not synthetically useful is although this reaction might give you a clean aniline, if you make any sort of change to the ring, like adding a methyl group over here, you actually will end up with a mixture of products. Where the amine doesn't necessarily show up where the leaving group was. These reactions go by an intermediate called a benzyne. So the mechanism of this reaction. The sodium amide is a very strong base. It wants to do a nucleophilic aromatic substitution, but the problem is this ring is just not electron deficient enough to accept the electrons. So, but what it can do, though, is this is strong enough to do an E2 reaction. And that gives us highly strained alkyne. And this particular molecule is called benzyne. Benzynes have actually been tracked and characterized, though it's very difficult to do so. And they've even been seen in outer space by various spectroscopic means. So this thing right here, though, is very, very unstable because the sp hybridized carbons want to be 180 degrees, but they're stuck at 120 degrees. That makes them incredibly reactive. Both of them are reactive, actually. And another molecule of NH2- can add to one of them. And this carbanion is very, very different from this carbanion of the Meisenheimer intermediate. The carbanion, the Meisenheimer intermediate, that lone pair is in a p orbital. It's resonance stabilized. The lone pair here is in sp2 orbital. It is not resonance stabilized. It's perpendicular to the pi system. And so, it's an incredibly strong base. What it does is it deprotonates the ammonia solvent. And gives this molecule. To get to the other molecule, the NH2- only has to attack the benzyne at the other carbon. And the resulting carbanion deprotonates and that gives you the second product. Now, an incredibly good research group actually went, and I have no idea how they did this. I wouldn't even know how to start how you would make a molecule, or let alone isolate a molecule like this. But they made this molecule where that carbon is actually carbon-13 enriched next to the chlorine. So they isotopically had a labeled compound like that. And then when they applied sodium amide and ammonia to this, the product they got was the aniline product. Where the carbon-13 was here and here. So this was just really an achievement in figuring out the mechanism of this reaction. Of course, both of these came from this benzyne. If it attacks on the same carbon-13, you get that. Attacks from down below, attacks from this side, you get the other one. Okay, that's all I have.